So in this chapter, we're going to solve different kinds of trigonometric equations. We're going to solve some, and we're going to prove some trigonometric equations, and we're going to start with that. So I'll show you an example first. So here we're asked to verify the following. That tan of theta cos of theta is equal to sine of theta. So how do we go about proving something like that? Okay, well, I wrote above the rule that you should, in general, follow. So to verify a trigonometric equation, we start with the more complicated side of the equation. So in our case, clearly the more complicated side would be the left-hand side. And rewrite the expression until it has been transformed to the expression found on the other side, which is in this case sine. So our goal here is to start with the most complex side and move to and transform it so that we can obtain sine of theta in the end. Okay, show that it's equal to sine of theta. So what's the more complicated side? Well, that's of course something you'll have to decide by yourself. There's no clear answer sometimes, but sometimes it's, I mean, there's it's more obvious than others. So here it's pretty obvious that it's the left-hand side. So we start with this, okay, and then what can we do to prove something like this? Well, we'll see that we have different tricks that we can use. But here we can observe that on this side we've just got sine. Here we've got cosine, we've got tangent. Now tangent is related to sine and cosine. So our goal is of course to get a sine of theta come out of the expression on the left hand side. And it seems that maybe if I rewrite tangent in terms of sine and cosine, maybe at least I will have a sine showing up. So that's the first good step, I think. So if I write sine, tangent in terms of sine and cosine, so tangent is sine over cosine, so that multiplies cosine, and then all of a sudden I'm like, oh, okay, that's okay. So I see why it's equal to sine. It's because these two expressions cancel out because they're common factors of the numerator and the denominator, and therefore this is equal to sine. So you see the idea, we go from the more complex expression to the simplest one, and basically at each step we try to simplify things until we reach our goal. I will show you in the book there's a nice list of the different identities we've seen so far that we can use. So this is on page 699. So you see the first three are the Pythagorean identities, which starts with cos squared plus sine squared equals 1. And if you remember, we can actually derive the other two from that one. So, so in theory, we should only be able, we only have to remember the first one. The other two are, the second one is obtained by dividing everything by sine squared in the first, and the second one, third one is obtained by dividing everything by cos squared in the first identity. After that, we've got the even odd identities. The ones I would try to remember are the ones for sine and cosine. So sine of minus theta is minus sine of theta, and once again, you don't really have to remember those. They follow basically from the geometry of the circle, and cos minus theta is cos of theta. Reciprocal identities, those are actually basic definitions actually of secant, tangent, and in terms of the other trig functions. And then we've got quotient identities, essentially rewriting sine, tangent and cotangent in terms of sine and cosine. And there are more actually that we've seen. So maybe at some point I'll show you like more identities that you can actually use. So let's take a look at another identity. Let's try to verify again that the product of 1 plus sine of x and 1 plus sine of minus x is the same thing as cos square of x. So that means, by the way, like if you replace x by any number, okay, this is going to be true, okay? And in particular, if you type this in your calculator, if you calculate this in your calculator and you calculate this, you should get exactly the same thing, okay? And it's true for all x, all values of x. Okay, so clearly here, this is the more complex side, so we're going to start with that. Now at this point, we could say, okay, we're going to expand this. That would be a valid first step. What also we could do is notice that we've got sine of minus x, and we know that we can rewrite this in terms of sine of x. And how is that possible? This is where I am sort of telling you don't have to remember all these identities that we've seen on the previous page. So if you recognize that if this is x, then this is minus x. It's the angle that it's the same as x, but essentially we rotate counterclockwise instead. So if this is going to be cos of x sine of x, so this is going to be cos of minus x sine of minus x, but at the same time these two are opposite, right? Because the y values are opposite to each other. The cos values are the same though. So this turns out to be the same thing as cos of x. The x values are the same, but the y values are opposite. So this is minus sine of x. So we can actually see our identities here. Cos of minus x is cos of x. Sine of minus x is minus sine of x. So you just have to understand the geometry of the unit circle, and there's no need to remember those identities by heart. So here we can replace sine of minus x by minus sine of x, like that. And then we can expand. And at this point, we notice this is like a plus b times a minus b. So we can expand very, very quickly here. We're going to get a difference of squares. We're going to get a squared minus b squared. And remember this notation, sine square x, that's the same thing as sine of x squared. So, so then we get this. So we get 1 minus sine square x. Okay. And at this point, we're trying to show that this is equal to cos square. So is there a relationship between cos square and sine square? This is one you have to know if you still don't know it. Like it follows from the fact that if I've got cos and sine here, since they lie on the unit circle, which has equation x squared plus y squared equals 1, then cos squared plus sine squared equals 1. So that's the basic Pythagorean identity. So there is a relationship between sine squared and cos squared. So let's see, we've got 1 minus sine squared. So we should send this on the other side. So cos squared is 1 minus sine squared. Oh, okay. Or I could actually say sine squared. Maybe that's even better for my purpose. Sine squared is 1 minus cos squared. So I can replace that in here. So sine squared is 1 minus cos squared. That's a basic Pythagorean identity. So this is going to be 1 minus 1 plus cos squared. And finally, you see I get cos squared of x. Here's another one. We want to show that, okay, secant squared theta minus 1 over secant squared is the same as sine squared. So the complex side is clearly this one. So I started with that. And try to see if you can do that one on your own. I would pause and come back if you can. Here are a few hints before you pause the video. And notice that on the other side we've got sine squared, and that's related to cos squared. So maybe if you can rewrite everything on the other side in terms of sine and cos, that's going to help. So maybe that's one thing, and maybe think about some of the Pythagorean identities. Okay. So hopefully we're able to do this. So one thing, well, I'm tempted to do different things. I could convert immediately secant, because I know secant is 1 over cosine. I could do that immediately, convert it, but then I get a complex fraction. So I'm not ready to get a complex fraction. So what I've decided to do here is divide each term in the numerator by secant squared. So secant squared over secant squared is 1. And then the next term is going to be 1 over secant squared. And then I've decided to convert secant squared, secant actually, into 1 over cosine. So this is 1 over cosine squared, like that. So this is 1 minus 1 over cos squared. And 1 over something is just the reciprocal of the denominator. So that's going to be 1 minus cos squared. And then again, I know that cos squared is, just like here, right? Cos squared is 1 minus sine squared. That's a basic Pythagorean identity. So this is 1 minus sine squared. So this is 1 minus 1 plus sine squared. And that's eventually just sine squared. Here we go. Okay, let's try another one. Here we're going to create an identity. So create an identity for 2 tangent theta secant theta by writing it in terms of sine only. Okay, so we started with this, and our objective is just to write that using sine. So what's very tempting to do here is convert everything in terms of sine and cosine. That's usually a good thing to start with. Try it out. So if I do this, I get this. So I clearly, by multiplying things out, I get 2 sine. So that's okay. The numerator is already taken care of. It's written in terms of sine. And the denominator is cos squared. Now again, I know that cos squared is related to sine squared. So that's going to help me write my denominator in terms of sine. So cos squared is 1 minus sine squared. And I'm done. This is written in terms of sine only. And the last example, we're going to factor an expression. So factor 4 cos squared theta minus 1. Okay, so we're going to factor just like we factor polynomials, except that we've got a trig function in there. So this is very similar to this, okay, where x is the cosine of theta. Okay, so how do you factor 4x squared minus 1? So that's maybe a first question to answer. Try to do that on your own. So this is the difference of squares, right? This is 2x squared minus 1 squared. So this is of the form a squared minus b squared. So it's going to give me a minus b, a plus b. So this is going to be 2x minus 1, 2x plus 1. So we can apply the same principle here. So 4 cos squared minus 1, that's 4 cos theta squared minus 1 squared. And this is of the form a squared minus b squared. So this is going to be eventually a minus b, a plus b. So I do that here. So, I made a mistake. This is not 4. This is going to be 2 cos theta squared, right? Because as you square 2, you get 4. So this is going to be 2 cos theta minus 1, a minus b, times a plus b. And I've used this here. Well, maybe I should erase it or rewrite it more clearly. So they basically, since a squared minus b squared is a minus b, a plus b. So as you can see, we can factor even some trig functions. Maybe last example, look, we can even factor something like that. So this one's very similar to 2x squared minus 3x minus 2, where x is sine theta. So if we can factor 2x squared minus 3x minus 2, we can surely factor that trig function. So the same rule will essentially apply. So we're going to try to find two numbers such that the product is minus 4 and the sum is minus 3. So what are those numbers? So minus 4 and 1 will do. So we split the middle term like that. We factor by grouping. So the first two terms, we group them, we factor them. So we can factor a 2, we can factor a sine of theta. So what remains is sine theta minus 2. And we're hoping that sine theta minus 2 will appear as we factor the last pair of terms, but it's already there. It's just sine theta minus 2. So this is just going to be, I'm going to put them in brackets just to know that they go together. And then finally, I factor sine theta minus 2. And what I get from that is sine theta minus 2 times 2 sine theta plus 1. And then I factor. So this is using the AC method, but on an expression that involves a trig function.